want to first thank you for making the trek all the way over here to Building C. I did not realize how far away this was when I saw it on the schedule, but thanks for being here with me to talk about the Istio project and hear about the latest and greatest that we've been working on. I'm Keith, I'm a principal engineer at Microsoft and a member of the Istio Technical Oversight Committee. And yeah, I'm here on behalf of the rest of the TOC to talk to you about this amazing project that we all know and hopefully love. So, to nobody's surprise, we're going to talk about AI. If you've been at KubeCon for this week and you've been reading the news, everybody's talking about it. So I figured we'd do a little bit of audience participation here when it comes to everybody's AI use. So when I could ask some questions and do a quick survey here. How many of you are serving AI models in Kubernetes today, either staging or prod? Raise your hand. Serving AI models. Okay. Good number of you, okay? How many of you hope to be running AI models in Kubernetes by this time next year? This time next year, hope to be running models? Another good amount of people, okay. Next 3 years, same group, about the same, all right. So maybe longer time horizon for some of you. Okay, how many of you aren't serving AI models, but you're consuming AI? So from OpenAI, Vertex, AI Foundry, Bedrock, how many of you raise your hand if you're consuming AI models from third-party providers? Okay, yeah, most, looks like the biggest group we've had so far. All right, shifting a little bit to agentic, how many of you are deploying MCP servers in your environments today? Raise your hand. Deploying MCP servers. All right. How many are planning to deploy MCP servers, but you're not today? Wow, I think we've got most people in this room fall into some of those categories. But just in case, if you haven't raised your hand yet and you don't want to feel left out, how many of you want nothing to do with AI or anything I just said? Raise your hand. Well, hey, I'll take it. Some of you are double raising. It's okay. It's fine. But my point with this is to say that no matter where you are in your AI journey today, Istio wants to be a part of that journey. And I think we can be. Well, some of the stuff we've been working on over the past couple of releases, we're doing some really cool things to bring Istio into the AI age. So the first thing I want to talk about today as far as our project updates is the Gateway API Inference extension. This is a new effort that's been kicked off within the SIG network. And hopefully, if you're using Istio today, or you've just been around the conference and hearing the talks, you're familiar with the Gateway API and Istio's support for it. It's a new standard way in Kubernetes to, well, not even new anymore, it's been around for a bit, but it's the standard way to describe traffic that's happening within and into a Kubernetes cluster. And in June, this past June in 2025, a new sub-project sort of adjacent to, a sister project to Gateway API, was created to build on top of it, to take all of the great work that's happened within Gateway API and bring it into sort of the AI world, and that's called the Gateway API Inference extension. Like I mentioned, it's a new sub-project within Kubernetes, and it extends the persona-based Gateway API model to include roles and personas that are focused on doing inference. And so if you see this diagram, a lot of this might be familiar to some of you. You're familiar with the Gateway API. You've got your cluster operators that are owning your gateways, your application developers who are programming routes to their services that they own, and then the Gateway API Inference extension adds a couple of new personas to this list. You've got your inference platform owners who are creating things called inference pools. And inference pools are, at their core, a backend type that you can route traffic to. And it represents a set of replicas that typically correspond to a model. And so one inference pool equals a set of compute for a model that's running inside a Kubernetes cluster. Within Gateway API, typically, you would route traffic from an HTTP route to a service, or from an HTTP route to a service entry if you're using Istio. With the Gateway API Inference extension, or GAIE, as we affectionately call it, you would route traffic from HTTP route to an inference pool. Traffic hits the gateway and then goes down to your model compute as you would expect. And on top of that, we also have a resource called the Inference Objective. An Inference Objective is a policy that helps you describe the relative priority of requests. So if there are some requests that come into your gateway, that come into your inference gateway, that are really high priority, or they're really tied to business value in some way, you want to make sure those requests are served by GPUs quickly and with lowest latency. Then you can tag it with a specific inference objective name, and it would take the priority that is defined inside that inference objective policy. And by contrast, if you had a request that came in that was not very high priority, somebody is telling the model, thank you, I need to send back an inference response, you can use that. That can take a long time. You can have that be a lower relative priority. And so these two new resources are the backbone of the inference extension. I want to get into a bit more detail here because there's a lot of moving parts to this extension. So one of the ways of thinking about GAIE is that it is a specialized routing architecture for LLM inference. So you've got the APIs that I showed you on the previous slide, the inference pool and the inference objective. But you also have a new architecture that is, like I said, specially for serving large language models. And so one of the things that's different about LLM inference, if you've done any work with it, you will recognize some of these, but it's not the same as regular REST traffic. It's got a couple of different properties and characteristics. For one, typically when we are writing proxies or we're configuring proxies and ingress gateways, the interesting stuff that we're using to route the traffic is based in the header, right? The header of your HTTP request. Well, with LLM inference and with the OpenAI spec, the interesting stuff that we're using to route the request lives in the body. And that might not sound like a big difference, but to a proxy, it's pretty massive. And so it means there's extra steps we need to do to be able to read that information within that body. The other interesting thing is that the resource utilization when it comes to cost of each request behaves totally differently than REST. How many SREs do I have? Like, raise your hand if you're SRE. All right, a couple of you. So if you're SRE or somebody who spends their day looking at dashboards and metrics, you're looking at CPU utilization that looks fairly even, right? You might get some moving up and down as you have some more requests or not, but it's typically fairly even, and you want low-ish CPU utilization. If you start seeing spikes on your graph, that means something's wrong and your heart starts beating, right? But with GPU workloads and AI inference, it's inherently bursty. Each request will almost completely saturate the GPU or the CPU for a given time because of the way that the inference process works. You're doing a bunch of matrix multiplication at the beginning of the inference request. And so that means that each request has an inherent cost to it that's going to saturate a GPU for a point in time. So we've got to think about that differently. And our algorithms we use for load balancing, like round robin, least request, are no longer sufficient for optimal global routing in those scenarios. And so the way that this inference extension is deployed, and we've got an image here you can see on the screen, it's aware of these differences. And so it's able to take this into account when deciding where to route traffic. And the thing I want to stress to you is that you can utilize this today. Let's look at this architecture here on the screen for a moment. So you can follow the numbers on the screen. You can see when the client makes a request, the first thing that happens is the chat request at /completions. If you use the OpenAI API, you're familiar with this. This is what you make a request to if you want an LLM to send a response back to you. You're completing a chat request that's being sent. That request gets sent to a Kubernetes gateway, a gateway that implements the Kubernetes GAIE, the Gateway API Inference Extension. And from there, we're going to do a thing called body-based routing. And body-based routing is what's going to allow us to peek into the body of the request in a way that a proxy never would traditionally, and route traffic based on those ever important details that live in that body. And once we've done that, and we've taken some of that information and put it into the header, we're then going to forward the traffic along to something called an endpoint picker. And this endpoint picker is basically an intelligent load balancer that sits outside of your proxy. And that's a bit different than the models that you might be used to seeing traditionally. But you'll see on the next slide, the effects of doing that is you're going to get vastly improved routing performance because the endpoint picker knows more information about where are the GPUs being saturated, what's the prompt size for each request. You can do a lot more intelligent things. And so once that endpoint selection step is done, the proxy is going to forward the traffic like normal to the backend, and it's going to be served as you would expect. And you might be thinking, if you're somebody who's worked in networking or even just software, there's a lot of callouts from the proxy to these extra services. And that looks like it's going to take a long time, and yeah, it does take a long time. But that's OK for us in inferencing workloads, because when I go to ChatGPT and I type in, hey, yeah, give me the works of Shakespeare ordered in the date they were published, it takes a good bit of time for that to respond. So because the cost, or the latency of inference requests is ordered in big O seconds instead of milliseconds, we can afford to do these external callouts to get better optimal utilization of our hardware. All that makes sense generally? Can I get some head nods in the room? Awesome. I know it's 4:45 and we're getting tired, but stay with me. I promise it'll be worth it. The beauty of this, by the way, is that that wasn't beautiful. But the beauty of all of this is that by using the Gateway API inference extension, we are able to still utilize all of the features of Gateway API that already exist. From header-based routing, path modification, et cetera, we can have an HTTP route that is bound to a gateway and have rules that are taking that request, transforming it, et cetera. So you don't lose hardly anything by utilizing this Gateway API inference extension. You can treat it as a normal request with extra features added on top. And so I've got an example here on the right where you can sort of see what this looks like in configuration. If you've programmed Gateway API before, in Istio or other implementations, this looks sort of familiar. You've got a gateway that's listening on port 443, matching hostname example.com. And then I would attach a HTTP route to the completions path to say, OK, requests that go to /completions, send those through to, and this is the new part, this inference pool resource. And that's going to select some compute. And then, of course, as we talked about before, the inference objective can change some of the properties of how high a priority that request is considered. And so if you think this sounds like a lot, you'd be correct, because it is. It's a lot to deploy, to a new mental model to think about. You might be asking, is it really worth it? Well, let the data speak for itself. How does that show up? OK, pretty decently. So when you do performance testing of this new architecture, compare it to regular Kubernetes service architecture, the results are pretty staggering. So on the far left here, we've got the sort of output tokens per minute. It's sort of a representation of throughput. And that stays pretty steady, even at 1,000 QPS as you scale up, because well, what that means is that you're not losing any throughput by using this new architecture. But the difference comes in when you start looking at the P90 of the per output token latency. The output token, you can think about it as each word the LLM spits out. And that per output token latency, as you start scaling up QPS, we're able to get a lot lower latency per token by using this new architecture. Because we're not going to be sending requests to GPUs that are starved. We're not going to be sending requests to GPUs that have a super long line. We're not going to be perpetuating head-of-line blocking. And then similarly, you look at the overall P90 latency of the request, not just per token, but the entire request. GAIE still performs better latency-wise compared to regular native Kubernetes serving. So that's a really brief overview of the Gateway API inference extension. And I want to tell you it's available in Istio today as of version 1.27. It's an alpha, so you've got an environment variable to switch on, but we'll be looking to promote this to beta soon. Please try it and give us some feedback. We want to be able to empower you to adopt AI in your organization with Istio. Moving right along, because that took longer than I thought. So we're going to move right along to Ambient Multicluster as far as another enhancement that we've been working on within the Istio project. My journey with Istio actually started with multicluster, fun fact. It's one of the more common reasons that organizations will turn to a service mesh. Istio is one of the first in the cloud-native ecosystem to have multicluster, and now we're bringing that same power to the new Istio Ambient mode. So you might be thinking, if you're not familiar, why multi-cluster? We're going to talk about that really briefly. The first reason is increased resiliency. You're able to reroute traffic away from unhealthy pods whenever you happen to have some degradation locally or even within a region. Unfortunately, cloud outages are a thing that we all have to grapple with and deal with to some extent. And so when you see degradation happening in one region or one cluster, you can detect those 500 errors and route traffic to healthy pods. Other reasons, if you're running active-active, you might want to do 50% here, 30% here, 90% here, 10% here to keep that secondary region still warm with data. That I've seen both of those at work before, and yeah, that's the reasons you might use multi-cluster. Another reason is extended capacity. Sort of in the theme of AI that we just talked about, what we're seeing now is an incredibly high level of scarcity when it comes to GPU resources. And so we don't always have the choice when we're looking for deploying GPUs somewhere. We can't say, oh, I want it in this region. I might need to just take wherever the GPU happens to be. And so in those cases, you're going to want to have a unified pane of glass to be able to send traffic, have that cluster, have that region interoperate with your existing infrastructure, because you need to go wherever the GPU is. And so running multiple clusters gives you a way to do that in a useful and a unified way. Next reason is distributed ownership. As I talk to organizations that are employing 5,000, 3,000, 8,000 engineers, sometimes a namespace per team model doesn't always work. So you might start spreading out to a cluster per team model, or maybe even multiple clusters per a single team. So if team A needs 3 clusters, and team B needs 1 cluster, or team C needs 5 clusters, you want those all to have a shared root of trust, but have some, how should you say, have each one be autonomous so that they can deploy what they need to, but still have some baseline level of policy and trust rolled out across your entire fleet. And so we see this a lot for governance in larger organizations. And then lastly, data locality. It's just a general principle, right? We want the request to be served as close to the customer as possible. By having multiple clusters, you can have data centers in your most business, the regions that are most important for your business. So if you are, most of your customers are in the Midwest, have a cluster there. If you've got 30% more of your customers in the West Coast, put a cluster there. And then their requests will be even faster when you combine the cluster with a CDN. And your customer experience is better end-to-end because it's faster and snappier. So that was a quick overview. Now that we've set the stage for why you want to do multi-cluster, let's talk about how Istio Ambient Mesh can help you reach those goals. So historically, if you've used Istio in sidecar mode, we've had 2 different ways of thinking about multiple clusters. One is called single network, where the endpoints in each cluster talk directly to one another. The other way is called multi-network, where to go across clusters, you go through what we call an east-west gateway that is sort of the entry points for service-to-service traffic across clusters. And today, I'm happy to give an update about our alpha-level multi-network support within Istio. And our goal is to bring it to production-ready status at beta next year. The reason we chose to do multi-network first over single network is because it's a more flexible approach. You can use multi-network on a flat, contiguous network, but you can't use single network on a disjoint network where there might be IP collisions and things like that. And so if you weren't at Istio Day 2 days ago, then you missed a great deep dive by Jackie and Steven here in the front row. I'm going to embarrass them. But they went super deep on explaining how the ambient multi-cluster support works. I can't go that deep on it today, but we'll have a bird's eye view of how this works generally. So on this diagram here, we've got a really basic overview of what the request path looks like. You've got a client that sends a request, and it's going to go cross-cluster. And because it goes cross-cluster, it goes to cluster B's east-west gateway, which then forwards the traffic on to the backends. And what's happening, one of the cool things about Istio is that every single one of these lines is encrypted end-to-end. And you can enforce identity policy at each step in this path. In this way, if you've got compliance requirements or just want to make sure your data is not being listened in on, you can use Istio to make sure it's safely encrypted end-to-end with the same transparent encryption and policy you're used to in single cluster mode. This is a bit more of an involved diagram where you can see every single proxy that's involved in this process. You can now see the Z-tunnels, the waypoints, all those things that you might be familiar with if you've seen Istio's ambient mode. These are the things doing the hard work of routing traffic in the cluster as well as between clusters. A couple of things I'll call out really quick. In ambient mode, the cluster administrator can define a labeling scheme for which services are considered globally routable versus which ones need to just be accessed by their local peers. And you can do that via an API called Service Scope. You define that sort of centrally for your cluster. And then what happens is that your application developers can then opt in or out of that policy by labeling their services. So what we have is a coordination between two different personas, two different roles that probably exist in your organization. And that way, you've got some sort of central policy, but also letting service teams move at their own pace when it comes to exposing their services globally whenever they're ready for it. And so once you label the service, the client is going to make a request. It gets intercepted by a Z-tunnel as regular ambient traffic goes. And then it's going to, if that remote service has a waypoint proxy for layer 7, the Z-tunnel will securely, through an encrypted channel, send that traffic to the waypoint. The waypoint then has a decision to make. Where should I send this traffic after I've done my path rewrites, my weighted routing, et cetera, et cetera? The waypoint can either send traffic to, do I have a laser pointer on this thing? I do not. That's unfortunate. But the waypoint proxy can decide, OK, I want to send it either to this local instance of my service, or I can send it to a remote version of my service. By default, because who wants to pay extra egress fees, by default, the waypoint's going to send that to the local instance of your service, or you should want it to send traffic to the local version of your service. But if that service has had, let's say 10 500 errors over the last 30 seconds, that's probably not super healthy. We probably don't want to send more traffic there. And so the waypoint can see that there has been 500 responses for the last 10 requests and decide, you know what? We're going to circuit break. Give that service a timeout and send it to the remote cluster's instance of the service. The waypoint will then send the traffic through the east-west gateway through a doubly encapsulated tunnel. The east-west gateway will terminate the first layer of that encrypted tunnel, check the policy, check the identity, and then, assuming that it's allowed through, send the traffic to the back-end Z-tunnel, which will decrypt the final layer of the traffic and securely forward it within the same net namespace to the server pod. And so that's, again, speaking general, high-level implementation of how that works. That's how Ambient Multicluster is going to function in your environments. Like I mentioned, we're utilizing a couple of Istio features that have always been there, and they still work really, really well. Things like outlier detection, weighted routing, failover, et cetera, will be respected by that local waypoint. If the local waypoint is down, we can also fail over to the remote waypoint. So this is a pretty extensible architecture, and we think that you're really going to get a lot of value out of it. So this is also an alpha, and we need your help to get it to stable. Please try it out. Visit the Istio GitHub page and give it a try in your staging clusters and see how this will work for you. We'd love to make sure we cover your use case. All right, lastly, but certainly not least, we're going to talk about default deny policies, every security engineer's favorite word. All right, so when you start talking about a default deny policy or a default deny security posture, a posture where you say that every piece of traffic is denied by default, and we're going to step-by-step allow list new destinations, it's really tough to accomplish, especially in a brownfield deployment. But I'm going to give you an overview of how you go about that. So the first step is having zero policy. This is where you're going to start if you're brownfield. You've got a bunch of services. They're all talking to each other, and you have no idea what depends on what. This is everybody's starting point. What you want to do is configure some level of network telemetry. Ideally, using Istio, it's a decent choice. Just saying, not biased at all. But yeah, configure some network telemetry. And that's going to help you get an understanding of your service dependency tree. I remember joining my last company and getting a sense of all the different deployments. And I asked a question to my boss at the time. And I said, how do you know which services depend on what? He just laughed at me. Because that's a hard question to answer in a lot of organizations, especially if you haven't had this built in from the ground up. So second step after the starting point is to figure out what services depend on what. Once you have that data, once you have a means to get that information, then you're going to roll out allow policies for internal service-to-service traffic. So go through and start explicitly allowing all of the traffic where you see the service dependencies. Depending on what tool you're using, again, using potentially Istio, you can make these audit policies as well, so that you can audit what services are talking to what services. But then after you do that, you're going to want to have explicit allow policies for all your internal traffic. That's typically some of the easiest things to identify. At that point, shift your focus externally. What resources are your services calling that are external to your cluster? What S3 buckets are they looking at? What blob stores on Azure are they requesting data from, or are they pushing data to? Your network telemetry should tell you those things as well, from IP addresses to host names, etc. Figure out what those external services are, limit those through policy as well. And then, when you're sure, and definitely not on a Friday, deploy your default deny policy to block all traffic that's not explicitly allowed. So some of the details may vary in your organization, but that's generally what the step looks like. Again, quick show of hands, how many of you are in step 1, where you just have no policy at all in your cluster? Okay, we'll get you there, I promise. Step 2, where you're looking at network telemetry, audit logging, you can at least see what's happening. Okay, folks at step 2, that's good. Step 3, how many of you have some sort of policy that allows traffic, or some selective deny policies in your cluster? Where are those people? I like that we're getting more people as we go down the line. That's good, it makes me excited. How many of you are at 4, where you're limiting access to external services? Nice, good. And finally, how many of you are at that almighty default deny policy in your cluster? We're working on it. Be like these people. We like this. We like this. But again, like the theme with all of this is an Istio talk. Istio can help you accomplish this. We can help you get from step 1 to step 2, step 3 to step 4, et cetera, all the way to step 5. And one of the specific ways we've done this in the latest releases is by allowing Istio's policy resource, authorization policy, to be applied by default to all waypoint proxies in your cluster. Here's how it works. So, first remember that in Gateway API, each gateway instance inherits from a specific gateway class. So in Istio Ambient specifically, you've got a gateway class that's called Istio Waypoint. And then every time you instantiate a waypoint proxy, you're going to be creating a gateway with gateway class name Istio Waypoint. So there's this inheritance structure that exists between your gateways and their gateway class. To make a default deny policy when it comes to your waypoints, you're going to create an Istio authorization policy in the Istio system namespace, because that's sort of the admin namespace for your mesh. And the target ref is going to be gateway class with the name Istio Waypoint. So you're binding your auth policy to the gateway class. You might be confused and say, wait, Keith, that's an allow policy. What do you mean default deny? Well, in Istio, we've got a precedence order that allows for some pretty complex configurations. And so deny policies take precedence. So if I make a deny policy, no allow policy can override it. So the way you create default deny policies in Istio is you create an allow policy with no rules, which means no traffic will match and make it denied. And if there's an allow policy, if there's one allow policy that is configured for a resource and the traffic doesn't match that, then that traffic's going to be blocked. So this is what default deny looks like in Istio. And I want to zoom in on this part. This is the magic, right? With policies and Gateway API, you're targeting a specific object. In this case, we're targeting that top-level gateway class. And so we're saying for all instances of Istio Waypoint that currently exist, that will exist in the future, this policy is going to apply. And then later, or even before, depending on the order you're doing this in, if I want to allow new traffic to a specific waypoint, then I can create an allow policy with specific traffic rules for a particular gateway instance. And you can see the target ref here of the gateway. The target ref from the policy is to the gateway of waypoint B. So also note I almost forgot, that to make this really work, you're going to also want to do a ztunnel workload level default deny policy. These gateway API policies operate at layer 7. You're also going to want to have layer 4 policies that are operating as well. That is all the updates I have for you at this point, but I want to stay in touch. I don't want this to be the last time we see each other. I'm clingy like that. Please come and join our very active community of users. We've got a ton of people on Istio Slack, both users and contributors, who are making the project better. And when you give us feedback, you are playing a role in making the Istio project better. So come to, I've uploaded these slides. They're on the Sketch website. Come join us in Slack. Come participate in Istio discussions. And make sure, if you're wanting to using these features, we want to make sure it works well for you. And lastly, if you have any feedback for me or on this talk, scan the QR code and let me know how I did. Thanks, everybody, and I hope you can go home and take a great nap tonight. See ya.